Hello and welcome to Astronomy Daily. I'm your host, Anna, bringing you the latest and most fascinating developments from across the cosmos. Today, we've got a great lineup of stories that showcase both human ingenuity and the wonders of our universe. We'll dive into SpaceX's 9th Starship test flight, a mission with impressive successes, but also some dramatic setbacks along the way. Then we'll explore a significant new discovery in our own solar system, a dwarf planet that's been hiding in plain sight for years and represents the largest such find in over a decade. We'll also journey to Europa and examine its potential future habitability, peek at a bizarre star within a star system, and investigate new research suggesting habitable moons might be more common than we thought. So get comfortable and join me for a journey through the latest astronomical discoveries that continue to expand our understanding of the universe we call home. First up today, SpaceX's Starship super rocket completed its 9th flight test recently, and it was quite the roller coaster of achievements and challenges. The launch began impressively at SpaceX's Starbase in Texas, with the massive 400-foot-tall rocket lifting off as planned. The first stage booster, known as Super Heavy, performed beautifully with all 33 methane-fueled engines firing perfectly, generating an astonishing 16.7 million pounds of thrust, more than twice the power of the Saturn V rockets from the Apollo era. What made this launch particularly notable was that this marked the first time SpaceX reused a Super Heavy booster, as this same first stage had previously flown during January's 7th test flight. The successful reuse represents a significant milestone in SpaceX's quest for rapid reusability of its rocket components. However, the mission encountered several significant challenges once the second stage, known as SHIP, separated from the booster. The planned deployment of 8 Starlink satellite simulators had to be scrubbed when SHIP couldn't open its payload doors. This would have been Starship's first ever payload deployment, making the failure particularly disappointing. Things went from bad to worse as SHIP continued its journey. As it headed toward a scheduled splashdown in the Indian Ocean, it began spinning uncontrollably. SpaceX commentators reported that the second stage had lost attitude control, apparently due to propellant leaks. The spacecraft ultimately broke up during its uncontrolled descent over a cleared area of ocean. Despite these setbacks, the test flight wasn't without its successes. The Super Heavy booster executed several challenging maneuvers after stage separation, including a directional flipover and maintaining a heightened angle of attack, both techniques aimed at improving fuel efficiency for future missions. The booster also demonstrated its ability to maintain controlled descent, even when simulating a single engine failure. SpaceX CEO Elon Musk remained characteristically optimistic, noting on social media that Starship made it to the scheduled engine cutoff point, which represented a significant improvement over previous flights. He also highlighted that there was no significant loss of heat shield tiles during ascent, another important achievement. Looking ahead, Musk indicated that SpaceX plans to accelerate its launch cadence for the next 3 Starship flights, aiming for approximately 1 launch every 3 to 4 weeks. This aggressive schedule reflects SpaceX's determination to rapidly iterate and improve the Starship system. This persistence is crucial given Starship's central role in NASA's Artemis program, where a version of the spacecraft is slated to serve as the landing system for the Artemis 3 mission, which would mark humanity's return to the lunar surface. Beyond moon missions, SpaceX has even more ambitious plans, with Musk suggesting that Starship flights to Mars could begin as early as 2024. While that timeline seems extraordinarily ambitious, the company's approach of testing, failing, learning, and rapidly improving continues to push the boundaries of what's possible in space exploration. Now let's turn our attention to discovery. In exciting news for planetary scientists, a newly discovered object in the outer solar system has been confirmed as a dwarf planet, the largest such discovery in more than a decade. Currently bearing the preliminary designation 2017 OF201, this celestial body measures approximately 700 kilometers, about 400 miles, across and follows an extremely elliptical orbit around our Sun. What makes this orbit particularly remarkable is its lengthy duration, taking an estimated 25,000 years to complete a single circuit around the Sun. This places 2017 OF201 in the exclusive category of dwarf planets, alongside more familiar objects like Pluto, the asteroid series, and a handful of other similar bodies in the outer solar system. The discovery story is almost as fascinating as the object itself. The dwarf planet was hiding in plain sight, buried within terabytes of publicly available astronomical data, some of which was collected more than a decade ago. Finding this celestial needle in a haystack required months of computational work to distinguish it from the countless background stars and noise. The detection came through painstaking analysis of data originally collected for the Dark Energy Survey, or DS. While that project primarily focuses on studying gravitational lensing in distant galaxies, the survey's ability to detect extremely faint objects made it inadvertently perfect for hunting distant solar system objects. Sihao Cheng from the Institute for Advanced Study led the discovery team, noting that while in principle anyone could have made this discovery using the public data, the process was extraordinarily demanding. Developing the algorithm alone took several months, followed by additional months of computation as they scanned through roughly 200 terabytes of data using hundreds of processors. What made the search particularly challenging was the widely separated observation dates. Unlike targeted asteroid searches that typically take successive exposures separated by hours or days, these images were often separated by months or even years, containing numerous points of light from unrelated objects that needed to be filtered out. After identifying the object in DES data, the team confirmed its existence by locating it in another public dataset from the Canada-France-Hawaii telescope. In total, they found 19 observations of the object spanning from 2011 to 2017, all showing it exactly where their orbital calculations predicted. The extreme elongation of 2017, OF201's orbit means it's only visible over a tiny fraction of its journey around the Sun, too faint to detect for more than 99% of its orbit. This suggests there could be many more similar objects lurking undetected at the edges of our solar system. Interestingly, this discovery has implications for the hypothesized Planet X, or Planet 9. Some astronomers have suggested this unknown planet's gravitational influence explains the clustered orbits of certain trans-Neptunian objects. However, 2017 OF201's orbit doesn't fit this pattern, potentially challenging the Planet X hypothesis, though debate continues among experts about what this new discovery actually tells us about our outer solar system. Next on the story list today. While Europa is currently an icy world with a subsurface ocean, its distant future might hold something remarkable. In about 12 billion years, when our sun exhausts its hydrogen fuel and enters the red giant phase of its evolution, the habitable zone of our solar system will dramatically shift outward from its current position. This cosmic relocation of real estate suitable for liquid water will eventually encompass Jupiter and its moons, potentially transforming Europa in fascinating ways. Researchers estimate that as the expanding sun grows more luminous, Europa could develop and maintain a tenuous water vapor atmosphere for several 100,000 years. The process begins with the sun's inevitable evolution. After spending billions of years as a stable main sequence star, our sun will eventually deplete its core hydrogen fuel. This triggers the fusion of heavier elements like helium, causing the sun's outer envelope to expand dramatically. During this red giant phase, the sun will grow hundreds of times larger than its current size, engulfing Mercury and Venus entirely, while rendering Earth uninhabitable. However, for the outer planets, this stellar evolution creates new possibilities. Computer models suggest that Jupiter's system will enter the red giant branch habitable zone in about 12 billion years, when it's approximately 2 astronomical units from the expanding sun, less than half its current distance. Jupiter itself will likely develop bright water clouds in its upper atmosphere as it experiences the increased solar radiation. More intriguingly, Europa's surface ices will begin to sublimate under the influence of both the brighter Jupiter and the expanded sun. Much like dry ice sizzling away in sunlight, Europa's frozen surface will transform directly from solid to vapor. While most of this sublimated ice will escape to space, simulations suggest some water vapor will remain bound to Europa for approximately 200,000 years before being completely lost. During this brief cosmic window, Europa might actually be considered habitable, though whether this time span is sufficient for life to emerge and thrive remains an open question. This scenario offers valuable insights for astronomers studying exoplanetary systems around sun-like stars. As we identify more exoplanets and potentially exomoons, understanding how these worlds evolve alongside their aging stars becomes increasingly important. The fate of Europa serves as a model for what might happen to similar icy worlds in distant star systems. Now for something pretty rare. In a remarkable discovery, Chinese astronomers have identified an extremely rare type of binary star system that gives us a glimpse into a fleeting phase of stellar evolution. Using the 500-meter aperture spherical radio telescope, also known as the China Sky Eye, researchers led by Han Jinlin from the National Astronomical Observatories of China detected a unique pulsar designated PSRJ 1928 plus 1815. Located about 455 light-years away, this system features something astronomers have long theorized but rarely observed: a pulsar whose radiation pulses are occasionally blocked by its companion star every few hours. What makes this discovery particularly special is that the two stars are actually orbiting inside a common envelope of hydrogen gas. Pulsars themselves aren't uncommon. Scientists have identified nearly 3,500 in our galaxy alone. These dense stellar remnants form after massive stars explode as supernovae. As they rotate, they emit beams of electromagnetic radiation from their magnetic poles that sweep across space like lighthouse beams. When one of these beams crosses Earth, we detect it as a regular pulse of radio waves. But the PSRJ 1928 plus 1815 system captures a critical moment in binary star evolution. In these systems, the heavier star ages faster and eventually collapses into a neutron star or pulsar. Meanwhile, the smaller companion star loses material to its dense partner, causing them to share a common envelope of hydrogen gas. For a relatively short period, astronomically speaking, the two stars orbit within this shared envelope. Over approximately 1,000 years, the neutron star gradually clears away this envelope, eventually leaving behind a hot helium-burning star orbiting the neutron star. This observation provides compelling evidence supporting long-standing theories about how stars in binary systems exchange mass, shrink their orbits, and eject shared gas envelopes. Understanding these processes helps astronomers piece together the complex puzzle of stellar evolution, neutron star behavior, and how such pairs eventually merge to produce gravitational waves. The discovery is particularly significant because binary systems are extremely common in our galaxy. More than half of all stars exist as part of binary or multiple star systems, their gravitational dance shaping their evolution in dramatic ways. In some cases, one star's gravity can drag material from its companion, leading to explosive events like novae or even supernovae. With increasingly powerful telescopes like FAST, astronomers hope to find more of these rare cosmic pairs, further illuminating the processes that shape stars throughout their lifetimes and after their deaths. Finally, today, while we've focused much of our search for extraterrestrial life on Earth-like exoplanets, a fascinating new study suggests we should broaden our horizons to include moons orbiting giant planets. Researchers from Hungary and the Netherlands have published compelling findings about the potential habitability of exomoons in the journal Astronomy and Astrophysics. Their study, titled Grand Theft Moons: Formation of Habitable Moons Around Giant Planets, used complex simulations to investigate how moons form around giant exoplanets and whether these moons could support life. The team, led by Zoltan Denks from the Hun Ren Research Center for Astronomy and Earth Sciences, focused specifically on the formation of large moons in circumplanetary disks, the rotating collections of material that remain after a planet forms. The researchers examined 461 known giant exoplanets, modeling how lunar embryos might grow through collisions within these disks. Their simulations revealed that moons with masses between Mars and Earth could form around planets roughly 10 times the size of Jupiter, with many potentially habitable. Perhaps most interestingly, the study found that the optimal distance for habitable exomoons is between 1 and 2 astronomical units from their stars. Beyond this range, tidal heating rather than stellar radiation becomes the primary heat source for these moons. This is similar to what we see in our own solar system, where moons like Europa and Enceladus likely harbor subsurface oceans warmed by tidal flexing rather than direct sunlight. The simulations also showed that as distance from the star increases, more moons tend to form, but their masses become too small to maintain habitability. Meanwhile, closer to the star, fewer but more massive moons form, with more being lost to stellar theft, where the star's gravity pulls them away from their host planet. While astronomers haven't definitively confirmed the existence of any exomoons yet, several candidates have been identified. The James Webb Space Telescope is currently examining potential exomoon candidates, and the European Space Agency's upcoming Plato mission may also be capable of detecting these distant moons. This research effectively expands our definition of the habitable zone to include moons orbiting giant planets. As one researcher put it, the circumstellar habitable zone can be extended to moons around giant planets, potentially multiplying the number of worlds where we might someday find evidence of life. Well, that's all for today's episode of Astronomy Daily. What an incredible journey through space we've taken, from watching SpaceX push the boundaries of rocket technology despite setbacks, to discovering a massive new dwarf planet that was hiding in plain sight within existing data. We've peered into the distant future, where Europa might briefly become habitable as our sun expands, and witnessed the bizarre spectacle of a pulsar orbiting inside another star. Perhaps most tantalizing is the possibility that habitable moons may be far more common than we once thought, potentially expanding our search for life beyond traditional Earth-like planets. Each of these stories reminds us that the universe remains full of surprises, constantly challenging our assumptions about what's possible. As our tools and techniques for observation continue to improve, from powerful radio telescopes like FAST to the upcoming Plato mission, we stand on the threshold of even more remarkable discoveries. The cosmos is vast and ancient, yet we're learning new things about it every day. Thank you for joining me on Astronomy Daily. I'm Anna, and I'll see you again tomorrow as we continue to explore the wonders of our universe together. In the meantime, keep looking up in wonder.